Welcome back. We will continue the discussion on the conservation law, and today we will proceed to derive the Lax-Volinic formula for a possible solution of the conservation law. Recall that in the previous class we discussed some special solutions of a conservation law, namely the rarefaction waves and shock waves, and these are solutions to an initial value problem called Riemann's problem. And Riemann problem consists of the scalar conservation law, in which the initial function consists of only two constant states. Okay, and now we'll consider a general bounded measurable initial function u0 and try to show that this conservation law has a weak solution. Uniqueness comes little later. Okay, so where we assume that f is C2 and uniformly convex. In the literature, there are many different proofs of this important theorem, that this uniformly convex conservation law has a weak solution, and our approach here is to use Lax-Volinic formula, and this Lax-Volinic formula in turn is derived from the Hope-Lax formula, which gives solution to the Hamilton-Jacobi equation. So Hamilton-Jacobi equation we have already studied in detail and derived this Hope-Lax formula and showed that indeed is a solution of the Hamilton-Jacobi equation. Okay, so again, so this is the Hamilton-Jacobi equation, Wt plus f of omega x, and again f is uniformly convex, and this is the initial condition given, Wx0 equal to W0x. Okay, to see the connection between Hamilton-Jacobi equation and conservation law, we proceed as follows. First, assume that this W, the solution of the Hamilton-Jacobi equation, is a C1 function. Though that is in general not true, we have only proved that W is a Lipschitz function, and by a theorem of Rademacher, then it follows that W is differentiable almost everywhere, and the Hamilton-Jacobi equation is satisfied only in the sense of almost everywhere. So here almost everywhere refers to a certain statement holds true except on a set of Lebesgue measure 0, either on the real line or on the in the plane in present case. Okay, let's see the connection. So this is just to get an idea what the Lax-Volinic formula looks like. Okay, so assume that the W solution of the Hamilton-Jacobi equation is C1. So then we can differentiate the Hamilton-Jacobi equation, that equation 1, with respect to x, and obtain this equation. Okay, for the first derivative, the derivative of W with respect to x, that is Wxt plus f of Wx x equal to 0, and Wxx0 is W0x x. Okay, so if you see, if you compare this equation satisfied by Wx and the conservation law, we immediately see that if we take u equal to Wx, then we have a solution for the conservation law. Okay, and to satisfy the initial condition, we can take W0 as integral 0 to x u0 y dy. Okay, and that in turn implies the first derivative of W0 is u0. So this we have to elaborate a little bit, because u0 is not a continuous function, it's only a bounded measurable function. So in what sense this is true, we have to see that. Okay, we'll see in due course. So in order to justify all these statements, we have to borrow many facts from the real analysis, and that is Lebesgue theory of measure and integration. So I will explain one by one as we proceed. Okay, so this heuristic argument shows that if we can somehow differentiate this W remember is given by the Hoppe-Lax formula, okay, and L is the Legendre transform of F, okay, this is also denoted by F star. So this given by this definition, supremum over x belongs to R, this product xy minus f of x. So this of course can be defined in Rn, and that's what we did in the discussion on Hamilton-Jacobi equation. So there you replace this multiplication by scalar product. Okay. So for example, if f(x) equal to half x square, and that is the case of Burger's equation, so an easy computation shows that Ly is equal to also half y square. So in this case, f and its Legendre transform are the same. Okay, in general, so since f is assumed to be smooth, okay, so this supremum is attained at y equal to f prime x, and since we are assuming f is uniformly convex, this f prime has a functional inverse, and so x is given by this inverse of f prime y, and just you plug in, so you get a formula for the Legendre transform. Okay, so formally we have this u of xt is derivative with respect to x of this wxt. Okay, and the only difficulty here is we cannot justify this differentiation directly, so we have to study this wxt given by the Hoppe-Lax formula and see in what sense this derivative can be taken. Okay, and for that we need to study this minimizer function carefully, and this minimizer function also arises when we simplify this formula in the end. So this plays an important role in the Lax-Olenek formula. So we need to study this minimizer. Okay, and of course that depends on x and t. So its minimizer is a function of x and t. So we'll first study how that minimizer depends on x and t. So that is our first topic. Okay. So this okay, for fixed so I state that as a lemma for t positive, let y equal to yxt be the minimizer of the right hand side of 2. So that is 2 is, again let me recall, that is okay. So you see that connection throughout. So this is Hoppe-Lax form. Okay, so you have to see this in together. Okay. Okay, so here I have written that wxt is equal to TLX minus YXT plus W0 Y of XT. Okay. So this W0X is the, of course later on we are taking, this is the initial function. So this initial function we are going to connect it to the initial function for the conservation law. Okay. So then the function x going to y of xt is a non-decreasing function. Okay. And this allows us to use a theorem of Lebesgue. So I will again state them in detail below. So this is Lebesgue theorem. So it's one of the important theorems in the theory of measure and integration. So any monotonic function is differentiable almost everywhere. Okay. So once that is known, so you can justify this. So this is wxt and this is given by this t of L x minus y xt. So L is a smooth function and W0 is also an absolutely continuous function. We will see that. So this W can be differentiated almost everywhere with respect to x, and that makes sense for this uxt. And since we are expecting this u to be only a weak solution of the conservation law, and that weak solution definition involves only an integral relation, so even almost everywhere defined function will be eligible for that weak solution, thanks to again the Lebesgue integration, which allows the integration of functions which are defined only almost everywhere. Okay. So proof of this lemma is quite simple, and it just uses the convexity of this L. Okay, so for your information, I have just recalled some definitions of the convex function. So you take any real valued function defined on an interval AB, so it's called convex if this inequality holds true. G of alpha x plus 1 minus alpha y is less than or equal to alpha gx plus 1 minus alpha gy for all xy in this interval AB, and 0 less than alpha less than 1. Okay. Suppose this g is a differentiable function, so we can simplify the convexity condition little bit. So these are easily provable things, and those are done in a course on analysis. So if g is differentiable, then g is convex if and only if g prime is non-decreasing. So this g prime is the derivative of g, and that should be a non. And it's if and only. Okay, so if g prime is non-decreasing, then g is convex, and if g is convex, g prime is non-decreasing. So we can still simplify further. So if you assume more smoothness on g, so if you assume that g is C2 and g is bounded away from 0 by a positive constant, so that is g double prime x greater than or equal to c, which is positive for all x, then g is convex and g prime is strictly increasing. Okay, so since by this assumption it immediately follows that g prime is strictly increasing because g double prime is strictly positive. So g prime is strictly increasing. So g is convex, g prime is strictly increasing. So in particular, this functional inverse exists. So this is functional inverse. So g prime inverse composite g, this is on their respective domains. Okay, so I am not writing that domain equality in that sense. Okay, so g prime will be from this interval AB onto some other interval, and g prime inverse will be defined on that range of g prime. Okay, so this a simple fact regarding the convex functions, and that's we are going to use, okay, this for our f is strictly convex, so f prime is strictly increasing, so this functional inverse exists. And as far as the Legendre transform is concerned, so that generally defined only for convex functions. So Legendre transform of G is also convex, and further if you take the Legendre transform of G star, then you get back G. Okay. So again back to the proof of this lemma. So what we have to show in order to show that that's non-decreasing, so take any two real numbers x1 and x2, x1 less than x2, and let y1 be the minimizer at x1 and y2 the minimizer at y of x2. So you just keep this Hope-Lax formula in mind all the time. Okay, so that's the major thing we are going to use and again and again. So in order to prove the lemma, we have to show that this y1 is less than or equal to y2. So in fact, we are going to show a little more. So what we are going to prove is this inequality for the Legendre transform. So this, remember, this L is Legendre transform of F. So it's convex. So that is convex. So we are going to show that this inequality holds. So T of L x2 minus y1 by T plus W0 y1 is less than or equal to. So just I put. We do not need strict inequality, so less than or equal to is fine. T of L x2 minus y by T plus W0 y, and this holds for all y less than y1. Okay. And once we prove this inequality star, and that implies y1 less than or equal to y2, because y2 is the minimizer corresponding to x2. Okay, and just again look at this Hope-Lax form. Okay, so we prove this inequality star. Okay, so you take any y less than y1, then we have these simple inequalities. So x2 minus y1 sits in between x2 minus y and x1 minus y1. Okay, so this x2 minus y1 is the thing we want here, and x2 minus y is the thing we want on that right hand side. Okay, so just so this x1 minus y also sits in between x1 minus y1 and x2 minus y. So therefore we can write x2 minus y1 as a convex combination of x1 minus y1 and x2 minus y, and that's what I have written here. And similarly x1 minus y as a convex combination of x1 minus y1 and x2 minus y. Okay. A simple computation shows that this alpha is equal to y1 minus y, x2 minus x1 plus y1 minus y. By the choice of x1, x2, y and y1, we immediately see that this alpha and beta both lie in the open interval 0, 1. Okay, that's what I meant by convex combination. Okay, so and this constants alpha and beta are related by, so alpha is equal to 1 minus beta, or alpha beta equal to 1. So now you apply convexity on this statement that x2 minus y1 is written as convex combination. So by convexity of L of, so now you divide throughout by T. Okay, so T everywhere it comes. So x2, L of x2 minus y1 by T is less than or equal to alpha L of x1 minus y1 plus 1 minus alpha L of x2 minus y by T, and similarly the second one. Okay, so these inequalities follow from the convexity of L. And now you add these two inequalities. Okay, and remember alpha plus beta is 1. So we get L of x2 minus y1 by T plus L of x1 minus y by T is less than or equal to L of x1 minus y1 by T, because these two are same, and alpha plus beta is 1, and L of x2 minus y by T. Okay, and again look at the uh, Hoppe-Lax formula. So there is a term containing the initial condition, so you just add that. Okay, so both sides you add this w0y1 w0y plus w0y1 plus w0y. Okay, so we are not changing the inequality at all. So even after adding that, we get the same inequality. So now I add this one to this first term. So L of x2 minus y1 by T plus w0y1 is less than or equal to. So now I take this term on the right and club with the first term. So this L of x1 minus y1 by T plus w0y1 minus, I take this one other side, so L of x1 minus y by T plus w0y, and the last term as it is, so L of x2 minus y by T plus w0y. And now y1 is the minimizer for that function and y is less than y1, so the term in the bracket, so this term in the bracket is less than or equal to 0, because y1 is the minimizer. Okay, so this is always less than or equal to that for any y. Okay, so this is less than or equal to 0, and so we get L of x2 minus y1 by T plus w0y1 less than or equal to L of x2 minus y by T plus w0y. And this is the inequality star, and that implies that y1 is less than or equal to y2, and lemma is proved. So this function x going to y of xt is non-decreasing. And now, before again proceeding further in the derivation of Lax-Volinic formula, so here are some facts from analysis we borrow. Okay, so here either g is a real valued function defined on an open interval, in that case it can be a whole real line, or it can be defined on a closed interval. Okay, so this is one of the important theorem of Lebesgue, so I was telling you. So this, if G is monotonic, then G is differentiable almost everywhere. So here monotonic means either it's increasing or decreasing, and this inequality holds. Integral a to b g prime t dt is less than or equal to. Okay, so when we have a everywhere differentiable function, the fundamental theorem of calculus say that this is equality. Okay, but in this case, so for almost everywhere differentiable functions, there can be strict inequality. So this is the first difference we observe between everywhere differential functions and almost everywhere differentiable functions. And this is a standard example, this Cantor function, which is constructed using the Cantor set. Okay, so I hope you all know Cantor, what is Cantor set. So using that Cantor set, so one construct this Cantor function defined on this closed interval 0, 1 to 0, 1. It's non-decreasing. In fact, its G is constant on those intervals removed in the construction of the Cantor set. So G0 is 0, G1 equal to 1. Okay, so in particular G is a non-constant continuous function. In fact, by continuity, G assumes all the values between 0 and 1. Okay, so G is non-constant, but one can show that this G prime. So since it's not decreasing, Lebesgue theorem asserts that it is differentiable almost everywhere, and G prime is 0 almost everywhere. Okay, so again, one more uh, feature of almost everywhere differentiable functions. So the derivative can be 0, yet the function can be very well non-constant. So that will not happen if G is everywhere differentiable. That we have in even elementary calculus, we observe that. Okay, and we also see that in this case, there is a strict inequality. So since G prime is 0 almost everywhere, its integral is 0, but this G1 minus 0 is just 1. So there is a strict inequality here. Okay, so the fundamental theorem of calculus, as we know from the elementary calculus, does not hold for almost uh, everywhere differentiable functions, and that is another important distinction. So for what sort of functions we can expect integration by parts? So we are in fact going to perform many integration by parts, so we should be careful for which functions this integration by parts holds, and that in turn gives the fundamental theorem of calculus for Lebesgue integral calculus. Okay, so here is one instance where this integration by parts holds true. So if G and H are from this closed interval to R are absolutely continuous, okay, so this is another subtle class of continuous function, so it's more than continuity, so it's called absolutely continuous function. So I am not going into details of that definition. Okay, then the integration by parts holds true. So namely A to B GH prime equal to GBHB and GAHA minus integral A to B G prime H. So if you take for example H is identically equal to 1, then we see that the fundamental theorem of calculus for the Lebesgue integral calculus. Okay, so that holds true. Okay, so this absolute continuity also implies differentiability almost everywhere, but then there is a equality here. Okay, so obviously that will tell us that this Cantor function is not absolutely continuous. Okay, and that brings us to another class of functions which we also need a little later. For example, we show that the weak solution of the conservation law is a function of bounded variation. Okay, so let me again briefly recall what is meant by a BB function. So again you take a closed interval and take any partition. Partition means so you divide that interval AB into finite number of points. Okay, and then you perform this variation. So you take the absolute value of g of xi plus 1 minus g of xi and then sum over all the intervals, subintervals. Okay, so this is called variation of G corresponding to the partition. Okay. So how this G oscillates in between the points. That's what it measures. So sometimes in fact it's called bounded oscillation also. Okay. So if we for any function, certainly this is a finite quantity, but what we want is, so we want to take the sum over all the partitions, okay, all the partitions, and take supremum of the sum over all the partitions, and if that is finite, then we call this G is a BV function, and this is called the total variation of G. Okay, this. So when you go to higher dimension, it will not suffice. So one has to obtain a alternate definition of this total variation. Okay. So this is the definition of a BV function. So if this total variation is finite, then you call it a BV function. And obviously, if G is either decreasing or increasing, so this we can remove this absolute value, and this sum will reduce to only at the end points. Okay, so obviously a monotonically decreasing or increasing function is function of bounded variation, is a BV function. And conversely, that's again in the study of PV functions you might have learned. So any PV function can be written as difference of two monotonic functions. Okay, and by again applying Lebesgue theorem, so this G1 and G2 are monotonic, so they are differentiable almost everywhere. So their difference is also uh, almost everywhere differentiable. So this G is differentiable almost everywhere. Okay, so this BV functions are also differentiable almost everywhere. And again, we can show that if G is absolutely continuous, okay, so then G is a BV function, but converse may not be true. Cantor function is an example again. And so this, if G is a Lifshitz function, certainly it's absolutely continuous. So this class of absolutely continuous functions sit between this Lifshitz continuous functions and bounded variation function need not be continuous, but continuous bounded variation function. Okay, and let me again state a theorem of Rademacher. So this holds even in Rn. So if u is a Lipschitz function in Rn, then u is differentiable almost everywhere, and this is what we have used in the study of Hamilton-Jacobi equation, because the solution given by the Laplace formula is only a Lipschitz function, so the Hamilton-Jacobi equation is satisfied only almost everywhere. Okay, and again I have written here. So for the conservation law, our weak solution satisfies this integral relation, and since this is only an integral relation, will be satisfied if this u and hence f of u are defined only almost everywhere. Okay, and that's what we are going to do. Okay, okay. So let me just okay. It's since it's going to take little more time than I expected. So from this point onwards, so we have now got a result on the minimizer, and that I will use to derive the Lax-Volinic formula, and then verify that the function given by the Lax-Volinic formula is a required weak solution of our conservation law. So I will take up this in the next class. Thank you.